So beautiful. See, it's my next cross. Okay, so we have this integral from 0 to 1 and fractional part of k by x and fractional part dx. And this was proposed by Ovidiu, Furdui, and from Kalamazoo, MI, in the School Science and Math Journal. Yeah, and k is a positive integer over here. Now, if you don't know about fractional part function, basically fractional part of x is defined as x minus floor function of x. And floor function of x rounds down x to the nearest integer. Let's say if we have 2.6, it rounds down to 2. If we have 2.99 as well, it will round down to 2. And let's say if we have minus 1.1, it will round down to minus 2. Just round down. Okay, now let's solve this problem. So how do you think we are gonna solve this problem? Basically, I will try to let y as k by x, and this will simplify the problem basically. And if I make this substitution, the integral now goes from k by 0 is infinity, and we will have k by 1 is k, and fractional part of y. Basically, k by 0 is undefined, but in the limit we can say that it's infinity. And now we know that x equals to k by y. That's why dx will be minus k by y square and then dy. Okay, so now after this we can take minus k outside, and now integral goes from infinity to k, fractional part of y, and then 1 by y square dy. Now there are some like standard techniques we involve when there are floor function or fractional part functions. Basically what we can do is, let's say if we have a to b fractional part of x dx, in that case we will basically write this in the form of sum, where n goes from a to, let's say, b minus 1. Yeah, an integral goes from n to n plus 1. Yeah, so basically from a to a plus 1, and then a plus 1 to a plus 2, a plus 2 to a plus 3. Yeah, so basically n goes a increases, n equals to a to a plus 1, when n equals a plus 1, a plus 1 to a plus 2. So basically now n is b minus 1, from b minus 1 to b. So basically we just have a to a plus 1 plus a plus 1 to a plus 2, and due to the linearity of integral operator, like this, all of this will sum up to an integral from a to b. This is how it works. And now g of x, sorry, fractional part of x now can be written as just x minus n, and this is how it simplifies. Yeah, because like fractional part n is just the g of x, because it's the smaller integral, like immediate smaller integer less than x. So this is fractional, sorry, this is g of x, and this is x, so x minus g is just fractional part of x. So this is the benefit of using this notation for solving fractional part integrals. And now let's solve this. So over here in this problem, what we can do is we can use the negative sign to reflect the integral first. So we have integral going from k to infinity of y, and then 1 by y squared dy. Yeah, now we can introduce a sum. Sum going from n equals to k to, let's say, infinity minus 1, so that's infinity again, and from n to n plus 1. Now g of y will just be y, so not g, fractional part of y will be just y minus g of y, and 1 by y squared dy. Now this can be easily integrated, yeah, and that is the benefit. So k sum from n equals to k to infinity, and integral from n to n plus 1 of 1 by y minus n by y square dy. Okay, Now after this we will have k times sum going from n equals to k to infinity. Now this is just ln of y. Now this is plus n by y. Yeah, from n to n plus 1. Sorry. Now you can easily evaluate this. Yeah, k sum going from n equals to k to infinity ln of n plus 1 by k, sorry, n plus 1, basically ln of n plus 1, let me do it, plus n by n plus 1 minus ln of n minus 1. Yeah, so now k sum going from n equals to k to infinity. Now this is just ln of n plus 1 by n. Yeah, and now this one is, if I take minus 1, this will be minus 1 by n plus 1. Yeah, if you like use minus 1 over here, so n minus 1, that's minus 1 by n plus 1. Okay, so now over here, now like what we can do is basically this over here is going to simplify, but let us say that limit t goes to infinity and their sum from n equals to k to t. Yeah, because I'll tell you in some time. Minus 1 by n plus 1. Okay, now we can like distribute the sum to each of them. So limit t goes to infinity. Now if this is going to sum from k to t, basically what we have is ln of k plus 1 by k, and then k plus 2 by k plus 1. Yeah, basically if we are adding the ln's, like that will just be product. Yeah, and it goes on up to t by t minus 1. Yeah, and basically all these will cancel out. So we just have ln of t by k. Yeah, so I can basically write this as ln of t minus ln of k. And over here now I can write this as, so basically summing from like n plus 1 to t, I can write this as h of t minus h of k. Okay, wait. Now over here, like since there's ln of t plus 1, so n plus 1 by n, the last term will not actually be a t, just t. Like I made a mistake over there. Over here the last term will be t plus 1 by t. Okay, I'm sorry for that. Yeah, because if it's t plus 1 by t will be there, into t plus 1 by t will be there, and the t cancels out. So this is actually ln of t plus 1 minus ln of k. Ln of t plus 1 minus ln of k. Okay, and now over here, also this goes up to t plus 1. Yeah, so basically now this will just be 1 by k plus 1 plus 1 by k plus 2 up to 1 by t plus 1. So this is basically like h of t plus 1 minus h of k. Yeah, okay, so yeah, I had made a mistake over here as well. T plus 1. Yeah, and if you don't know about like what this h of e is, basically this is known as harmonic number, and this is just a notation. Basically this is just a notation. H of n is actually the sum of the reciprocals up to n. Okay, up to n, this is it. Okay, so now this is h of t plus 1 minus h of k. Okay, so now we have k, and limit if t is going to infinity, t plus 1 also go to infinity. Yeah, I can write that. T plus 1 goes to infinity, plus 1 is just infinity. And we have ln of t plus 1 minus h of t plus 1 plus h of k minus ln of k. Okay. Yeah. Now what do we do? Okay, now this thing over here is a standard limit like idea. This over here. So basically, limit of x tends to 0, x the harmonic number minus ln of x. Like when x is larger, this difference tends to a number, a constant, which is like Euler-Mascheroni constant. Yeah, so this was found by Euler, I guess, that this actually approaches to number, like just like this limit x goes to infinity of 1 plus 1 by x to the power x. This also approaches a number, and the number is Euler's constant E. This also approaches to a number, and that is Euler-Mascheroni constant. Okay, so now we know that this is actually the like reverse of the expression. That's why this will be negative of Euler-Mascheroni constant and plus h of k minus ln of k. Is that it? Minus Euler-Mascheroni constant plus h of k minus ln of k. Okay, so this is the answer, like object from the answer key. Now let's see the special case as well. The special case when k is 1. So if k was 1, now we want the integral from 0 to 1. So integral from 0 to 1 of fractional part of 1 by x dx. So this would have been let's put the k equals to 1, negative of Euler-Mascheroni constant plus h of 1 minus ln of 1. So ln of 1 will be 0, h of 1 will just be 1, so 1 minus Euler-Mascheroni constant. What a nice and beautiful answer. Yeah, so basically for this special case, the answer is truly beautiful. 1 minus Euler-Mascheroni constant. Yeah, so simple, but like such a beautiful solution development. And yeah, this was the answer. K times h of k minus ln of k minus Euler-Mascheroni constant. K times h of k minus ln of k minus Euler-Mascheroni constant. So hope you enjoyed the solution. If you have to talk about the flow of the solution, we basically first of all used the standard approach to fractional part integrals. I also gave you introduction of the fractional part integrals and the linearity of integrals and how we can like arrange it into a sum. And then we used that technique, and then like took integrals, evaluated. This was telescoping sum, and this was the this involved the harmonic number. Now there was a standard limit problem, and we used that and we got the answer. So this was it. Hope you enjoyed the problem, and thanks to Ovidiu for such a beautiful problem. And yeah, I look forward to seeing you in the upcoming videos too.